In this module, we're going to talk about remote sensing and aerial photography. Okay, we'll cover this fairly quickly. Then we have one more lecture, we'll have lunch, and then we'll go back to what's going in the labs. What you're going to learn on this module is the basic principles of remote sensing, aerial images, quality of images, uses of aerial imagery, stereo images, and satellite images. The whole idea of remote sensing data is really, in terms of GIS, really means anything from space. So, for example, those samples there, those are satellite imagery from space, so Persian Gulf and Iceland or Greenland. Okay, and then the next image there is Texas, Corpus Christi, and then the bottom one with the little red dots, those are irrigation using infrared. These little red, that's wet and infrared imagery of what we call pivot irrigation. That's why it's round. In North America, we have quarter section. Each pivot is probably a quarter-mile square piece of land. Each circle has a diameter of 400 meters, radius of 200 meters. What we call pivot irrigation. Infrared, this is the same picture in color, RGB. So you can see that the pivot area is very green because there's water. Remote sense data, you have aerial imagery from aeroplanes and drones, and then you have satellite. Yeah? So with the satellite, you can cover a big area, large area. You also have what we call spectral range, so different bands of light frequency, visible and infrared and invisible spectrum to the light spectrum. So then you have basically geometric accuracy and Alright, so principles of remote sensing. Remote sensing is based on reflected electromagnetic energy. So it's reflected light from the ground, the sun to the ground to the sensor. Okay? Each color of light has a different wavelength. And the whole range of wavelengths is called the electromagnetic spectrum. So what we can see, we can only see a very small band of the spectrum visible for our eyes. There's more lights than we cannot see. So if you go online, you can learn more about the electromagnetic spectrum, you can learn more about light waves. And so this is an example of the spectrum. So this is, for example, the range of the electromagnetic spectrum. This little part here is what we can see. You take the visible part of the light, this is what it looks like, and if you use the other parts of the electromagnetic spectrum, you can get a different image of the same field. So, for example, if you look at this, just within the visible light, everything looks green, for example. If you use infrared filter, you can see that the red is healthy, so this part of your field is not very healthy. And in this case, they're saying that the reason this part is not so healthy is the high salt content in the ground. Okay? Salinity is the problem. In southern Alberta, where we have the plains, the steppes, equivalent of the Mongolian steppes, we have a lot of areas with salinity problems, so it's not very healthy for plants. Right? So if you did remote sensing using infrared, you can tell which part of the farms are not good because it's too savory, too salty. There are two types of remote sensing, what is called passive and active. So the passive remote sensing relies on the sun energy, the reflection from the sun energy, and it will not penetrate clouds. Clouds would affect the passive. So if you have clouds, you can't see it. Active remote sensing is something like radar. Radar is a certain frequency of the light spectrum. It generates an energy signal, detects the energy return. Active systems like day and night typically penetrate clouds. Radar is the most common active remote sensing system. For the normal light spectrum, if you're in the satellite and there's clouds, you've looked at Landsat data where you have clouds, you can't see below the clouds because the light frequency is reflected on. But if you have radar, it will penetrate the clouds. It uses a different frequency. However, for example, in Canada, we have in the east part of Canada, we are worried about icebergs from the Arctic coming down and affecting the ships. So the Canadian government developed RadarSat, which is a satellite remote sensing satellite that uses radar. And because with the coastal situation and the icebergs, you also have clouds in winter, so the normal satellite will not see under the clouds. But radar said we can pick up the icebergs through the clouds. So that way the Canadian government can observe if there's icebergs to warn the shipping. So the other type of active is LiDAR. LiDAR is also a type of radar, and it is actually stands for light detection and ranging. This is now very popular, and it has a higher resolution than radar. It uses a more focused beam, and we do a lot of LiDAR remote sensing aerial mapping in Canada. Probably the States as well. And we use it to generate 3D ground surface for construction, etc. Okay, it's good for contour mapping. Okay, so aerial imagery. This is the old days where you have in a plane, the front of the plane, so you're putting a camera in the nose, aerial camera. This is another type of camera. I think this could be a TV camera actually. And then drones. Much more sophisticated drone than what we had with a launcher. And then I think that's a quadcopter, if I'm not mistaken. Okay, on the right side. Okay, so aerial image attributes. So we have an image scale, extent, and image resolution. So if you remember, if people here use Landsat imagery is around 30 meter pixel. Panchromatic in the Landsat is 15 meters. Panchromatic is black and white. And then they also process the panchromatic against the color bands, and they have pseudo 15 meters. So for our drone, for example, DJI drone, our image resolution, you go from 30, 15, for the DJI 6 centimeters, yeah? So image scale, 1 inch to 100 feet, so it just depends on how big your image is, okay? In our case, we're really talking about satellite, each scene. But in the DJI, we've got each frame. We use it, process it into one big map, orthophoto. So it's a little different. You know? I think that's not quite relevant for us unless you're using a satellite image. You know? Extent, physical size of recording media, lens system, flying height. A satellite image is quite large. The photo width of a satellite image could be hundreds of meters wide. In the case of the drone, it would depend on the pixels, right? If, say, it's 5 centimeters times 4,000 is what? Well, we have 4,000 pixels across, and if each pixel is 5 centimeters, how wide? So our drone covers the extent is about 200 meters wide. Resolution, so our resolution, for example, is 5 centimeters plus or minus. Image resolution, so obviously the smaller the pixel, the sharper the image. Panchromatic. Now this is back to cameras and planes. In the past, we have film. Now almost all the aerial is done digitally. Digital cameras, so we don't deal with film anymore. Typically in the past, you have either black and white, true color, or infrared. But today now, what happens is that we almost don't have panchromatic anymore. It's color, and then we have filters for infrared, okay, sensors. So we have different sensors. So now then digital cameras, so these are your sensors. So inside the DJI drone, we have a Sony sensor, and essentially it has different layers for the sensor, and it basically converts image into color pixels. It's like a TV. And the sensor has different layers, and basically the colors affect the sensor, and that's how it captures RGB and so on. If you want infrared, then you need to put a filter on the sensor. Geometric distortion, because every camera has a lens, and the lens towards the edge will have distortion. Perspective. Normally when we fly the drone for aerial mapping, the camera points down vertically, and we're trying to capture the Earth directly looking down. Perspective is if it's, say, at an angle of 45 degrees, that would be perspective. So primary source of aerial image distortion. So the terrain, camera tilt, film deformation. So these all these can affect how your picture is distorted. So basically they're saying the film or the sensor, the camera lens, the atmospheric and other camera errors, these are minor. The camera not being perpendicular, or if the drone is being blown by the wind, like our big fixed wing. So the tilt would affect your distortion, and the terrain. So if the terrain is up and down, there'll be more distortion. If the terrain is flat, there wouldn't be as much distortion. And I think Batya can show you, when you fly the city with the buildings, because they're up and down, that will create distortion. And when you process in EdgeSoft or something, you'll see some weird distortions in the orthophoto. Now just be ready to get some distortions that happens. Terrain distortion, I wouldn't say too much about that. Other than if you have elevations, then you have more potential. The scale changes because the land is closer to the plane or further away from the plane. All right. So the last point is kind of important. The vertical aerial image taken over varied terrain is not orthographic, which means if you have bumps in the terrain or buildings, it is not orthographic because it's not uniform. There'll be too much distortion in the pictures. So this means that if you're in mountainous areas, it's harder to get a good orthophoto made and measured. Camera tilt, if you recall, the wind blows and the plane, you can see it actually moving sideways. When it does that, then the camera is not pointing straight down. That is worse on a fixed wing than on a drone because of the gimbal. The drone gimbal will actually correct for the drone tilting. But in a tough wing, we had no gimbal, so it does not adjust. So we can discuss these errors, but there are a bunch of errors that would affect your orthophoto image production, your map production, and then geometric corrections. So when we do an orthophoto, we do geometric corrections because we also get the 3D mesh of the surface, and that mesh is used to try and correct the photo pixels. So we do some geometric correction, say with EdgeSoft or Open Drone Map. Photo interpretation. So photo interpretation is you taking the images and you're trying to generate information out of it. You may interpret, try to find out the rivers or the creeks or the valley bottom, right, with the photos. So that's photo interpretation. Ground truthing. With satellite images, for example, a satellite image of some farmers' fields, show you different colors of green vegetation. So you can't tell from the satellite whether the dark green is corn or the light green is wheat. What happens is that you have to go to the field and actually observe from the field which is corn, which is wheat, and that's called ground truthing. So when we work on this exercise, then you can see what we're talking about in terms of ground truthing. End lap and overlap. Okay, when we did the autonomous flight planning with drone deploy, if you remember, each photo overlaps the other photo. You need overlap to generate the mosaic, and then you got what is called overlap and end lap. 3D, we're not going to bother too much with 3D, but just for concept, when you go in to see a 3D movie, you have the red and blue glasses, you get to see stereo. Or you can use polarized 3D glasses. I think nowadays in the cinema, when you go to the IMAX, I think it's polarized 3D glasses. Stereo model. So later on you'll see that we can actually, with the 3D, we can get the stereo model, just with shading. And this is without glasses. This is just the brain thinks that you can looking at a 3D object. Satellite versus aerial images. Satellites have high spectral ranges beyond film, very high perspective. So you can have many sensors on the satellite. You can measure many parts of your electromagnetic spectrum. And the aerial, you may or may not be able to do that. Generally, you will do color, RGB, on the sensor because it's like a camera sensor. You can have filters to make it a little better. The other part is because the satellite's so high up, you have much less distortion and you have much higher perspective. It's much flatter looking. If our drone is low down, the bumps is exaggerated. So these are the different satellites, Iconos, Landsat, and MODIS. I think MODIS is 500 meters? So the MODIS is quite coarse. I think it's 1 kilometer, half kilometer. Landsat's 30 meters, 15 meters. And Iconos is going to be smaller, maybe sub-meter, meter. It's academic, we'll look at price, cover big area, takes time to process, etc. for satellite. It's nice to get satellite, but usually it's too expensive for us here. So for the smaller area coverage, drone is probably the easiest way for us to get current, up-to-date aerial mapping.